And here we are, at last, final chapter, 26, last inference procedure. Very exciting. So it's been a while since we've done linear regression information. So we start really normally with some sort of a linear regression model. So we have a scatter plot of some quantitative data. We can tell strength form direction. We have a strong positive linear association between this variable and that variable. We can talk about the strength of the association using an R value. We can talk about the percentage of variation in Y that can be explained by X. That's the R squared value. So we've learned how to look at a scatter plot, tell if it looks linear or curved. We've even learned how to fix curves using some re-expression. So all of that we review on the side ahead of time, just to kind of pull all that information back out. So now that we've had a chance to do an activity in class where we've reviewed the big ideas for linear regression, we get into the actual inference procedure. And there's only one. The inference procedure for regression is a test for an association between two variables. So we're going to dig right into that with this first slide. So which test you use, the very first determination is what kind of variable you're working with. If you're working with a categorical variable, you're in z-test world or chi-square test world. If you're looking at a quantitative variable, you're always in t-world. So that makes it kind of easier in that there's always one world to be in for anything quantitative, anything with units, anything with means or units. So we just learned in the last chapter the chi-square test for independence, and that is a test for an association between two categorical variables. So in categorical world, we do chi-square tests. In quantitative world, if we want to test for an association between two variables, beyond just, oh, here's a picture of a scatter plot, it looks like there's a strong association between the two variables, we want to be able to quantify how strong that association is, and if it's strong enough indeed to be able to say that it's statistically significant. So that leads us to a test for an association between two quantitative variables, and I probably should underline that word association too. And so we need a regression model and a regression test, and that's the last one we're going to learn. Now, the good news is, and I actually typed this out because good news is worth some paper and ink, the calculator or computer program will do all the computations for regression inference. You will do 0 computations, none, not even one computation will you do. It'll find the regression equation, your least squares regression line, your literal, your y hat equals a plus bx. It'll graph your scatter plots and your residual plots. So the pictures will already be there. You won't have to crunch those out on your calculator on AP Exam. On AP Exam Day, they'll have all those pictures already on the paper, and you have to talk about what you see in those pictures. So the picture of the scatter plot looks relatively straight, and the association looks relatively strong. The picture of the residual plot has no pattern. And so that means that we have a good model, an appropriate model. And then we also look at the standard deviation of the residuals, the amount of spread in the residuals, and make sure that it looks nearly normal. So we're going to add that little check-in as we go. But all of those graphs will already be there. We just have to talk about them. The computer program or the calculator will calculate the t-score. It'll calculate a p-value. And it'll tell us any kind of other pieces like standard deviations or standard errors, degrees of freedom. All that business will be computed and given to you. Typically, it will already be on the paper in sort of a computer printout form. So we need to get accustomed to looking at those again. We've seen them before, but now we're going to dig into the bits and pieces that we kind of skipped over before. And the name is pretty straightforward. It's a linear regression t-test. Quantitative, always t-world. There's a t-model that has a number of degrees of freedom that backs it up. So we're back to the old t-model, the trusty t-model that we used in the earlier chapters. Even better news is that on the AP exam, that they'll already have everything summarized. and you just have to write hypotheses, maybe check conditions, although oftentimes the question will say assume that assumptions and conditions have already been met, which is fantastic, and we don't have to check them then. Jot down the name of your procedure, linear regression t-test, no matter what, and then do your t-square p-value and write a conclusion. So mechanics wise, it's really just listing what's in the computer printout. So the order of the day is, can you fish the information out of the computer printout that you need, because you're not going to use your calculator to get it. Okay? So since it's always a test for association, the hypotheses are pretty much written in stone. They always look just like those independence hypotheses in the chi-square test, but you've got to be very, very, very vigilant about making sure there's a word in there that's really easy to leave out. You don't have this word in chi-square test because you don't have scatter plots in chi-square tests. There's no linear association between the x variable and the y variable, whatever they are in context. And then there is a linear association. So nothing interesting is going on versus something interesting is going on. Now, if we think about a picture of there is something going on and there isn't something going on, it's really about a slope. Let me come back to that in just a second. I'm getting ahead of myself, so pause and let me just go with this. So hypotheses written in stone, they look the same every single time. We're just going to practice writing them. Conditions, totally different than the conditions we check for other tests, because it's an entirely different picture of data, an entirely different relationship. So there's 4 conditions that have to be checked. Hopefully we won't have to check them on the AP exam because it will say that the conditions for inference have already been met. But if they ask us to check them, the pictures are going to be there and they're going to be in the right order. So the first picture they're going to give us is going to be a picture of the scatter plot, the original scatter plot of x versus y. And we look at it and say, does it have a curve? Does it have a fan shape? Is it kind of straight? So we check to see if the scatter plot is straight. And so all we would say is we'd look at the picture and then we would say if it's straight, the scatter plot is reasonably, nice weasel word, linear. Or it's not reasonably linear. It has a curve in it. And if it has a curve in it, stop right there. Don't do an inference procedure. It doesn't make any sense to even make a regression equation if there's a curve there. So before you could run any kind of inference procedure, you would have to re-express the curve with logarithms or powers or something like that. So you would not proceed at all. They're not going to give you a test to run on the AP exam that's built on a curve. So it's going to be reasonably linear, and you're going to say so. It's that simple. Then we have to assume that each point in the scatter plot is independent of other points. Well, that's about the residual plot. So the second picture that's going to be given to you in your problem stem is going to be a picture of the residual plot. If your residual plot has no patterns, that not only means that this was a linear model is appropriate, but it also means that your points are independent of each other. There's not something interesting going on. So the independence assumption is basically checking and make sure the residual plot has random scatter. So you would say the residual plot has random scatter or no pattern or something like that. So is your scatter plot linear? Check. Is your residual plot random scatter? Check. We check for that anyway. And the pictures will be there, and they'll be there in that order. So you're basically commenting on all the pictures that you're going to see. And then the plot thickens assumption, that whole fan-shaped issue, you cannot have a fan-shaped residual plot. If you have a fan-shaped residual plot, then your model is not worth the paper it's written on. So you check your residual plot for a fan shape. So these two kind of go hand in hand. Those are based on the residual plot. So the residual plot has consistent left to right spread. Okay, so no fan shape. But we want to use good terminology, so consistent spread is how we really want to say it. So first conditions based on the first picture you're given. Second and third conditions are based on the second picture, and they can be combined into the same sentence. You can say the original plot has random scatter and consistent spread in the same sentence and kill two birds with one stone. Two conditions with one sentence. The last one, which is always the last one except for chi-square, where we don't have a picture that looks like a bell-shaped curve, is the nearly normal condition. And instead of checking sample size, that doesn't apply here, because this is really about the picture. They will show you a picture of the residuals of the a histogram of the residuals, some sort of a histogram, dot plot, something of the residuals. So you look at the picture, and if it looks fairly unimodal symmetric, doesn't have outliers, doesn't have any skewness, that's substantial, then you're good. So you check to see if the picture of your residual histogram looks unimodal symmetric, not terribly skewed. And you say something about it. So you would say something like the histogram of the residuals, you don't have to draw it, they'll draw it for you, is roughly symmetric with no outliers. Hopefully it's unimodal as well. If it's bimodal, we have a problem. Let me squeeze that in there. So you have three pictures. You've not seen them yet, but we're getting ready to in just a few minutes. You have three pictures, and you comment on all three pictures, and you've checked your conditions. So conditions are comment on the three pictures they gave you. Okay? If those three things check, then you would say, okay, check, 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 do a linear regression t-test. If they tell you the conditions have already been met, you just state the procedure and move on. Always state the procedure. Name the procedure is always there anytime you do an inference procedure. Okay, so we've got hypotheses, we have conditions. 2 done, 2 to go. Moving right on. So here's what we need to know about the t-test. What's really going on? So I'm giving you this stuff, but you haven't seen any pictures yet. You don't really know what you're testing. So let's dig into sort of the big idea behind this test. The linear regression t-test is a test about the slope of the regression line. Here's the idea. The null hypothesis assumes that there's no linear association. No linear association. Okay? So what would that scatter plot look like? All right, well, let's draw a scatter plot with no association. No linear association means you do not have any kind of a distinct linear pattern. Okay, or you don't have a curve that needs to be re-expressed. So, you know, in a perfect world, you'd have something that's just like a ball of points. Kind of just if you drew an oval around it, or attempted to, it wouldn't line up. It wouldn't make a line, it'd just make a ball. If you tried to fit a regression model through here, if you gave the calculator that set of points and said, give me a least squares regression line, do a regression model, it's going to give you a line that's horizontal. So your y-hat line, your least squares regression line, is going to be flat. In other words, it's going to have a slope of 0. Okay, so slope equals 0. And the slope is in the a plus bx formula for y hat that's in the blue book now. B would be a 0. You have a slope of 0. So just be y equals a. Y equals a number. And the 0 times x would just go away. Now you're not going to have to deal with the formula so much as just the fact that if you had no association, there would be not a linear pattern and the slope would be 0 for your least squares regression line. So the assumption is that your slope is 0. You can even say that when you're at our hypotheses, but it's not necessary that you do. Okay? If there is an association, if the alternative is true, there is a linear association. So if your points line up, either positive or negative, does not matter. If your points make some kind of a picture where you can fit a straight line to it and it makes sense, that straight line will have a slope that's not zero. If it goes down, it'll have a negative slope. If it goes up, it'll have a positive slope, but there will be a computable slope. So your slope would not be equal to 0. So your b would not be equal to 0 in this one. Your b would be equal to 0 up here. So the variable in question is the variable b. Is the slope 0? Is it not 0? If the slope is 0, nothing interesting is going on between these two variables. If the slope is not 0, there is something going on between the two variables. Not just something going on, but something quantifiable, something that we can actually write a rule for and make predictions with. So, if the scatter plot has no discernible linear pattern, that's the scatter plot itself, that's x versus y. X versus y, the actual scatter plot of the two variables. If there's no pattern, the slope would be 0. A slope of 0 would support the null hypothesis of no linear association. And if the slope of the least squares regression line is different enough from 0, not 0 enough, the p-value will be small, and we would reject the null and roll with the alternative instead. That's the reasoning behind it. We're looking to see if there is a discernible linear association, so we're looking for evidence for the alternative. That's what we're always looking for. We're trying to convict somebody every single time, so we're always looking for support for this second one. So, when you do the test, we've already looked at the hypotheses, we've already looked at the conditions. The third thing is going to be mechanics. So in mechanics, there are three pieces that have to be there. Degrees of freedom, if you do a chi-squared or a t, and then the actual t statistic, the test statistic, and a p-value are going to have to be involved. So since you're testing a sample slope, and b is the variable that we typically use for the slope, it's the number in front of x in your formula book, against a slope of 0. Now, we're arguing that in a perfect world, if there's no association, the slope would be 0. Perfect world uses Greek letters, and so the Greek letter beta would be 0 in our assumption, our null hypothesis. But we don't normally write that down because we usually do it in words. But we're testing a b, not Greek letter, the observed slope, against the expected slope, which is generally 0. So there's a t here that doesn't belong. I don't know why. Just scratch it out. Your t-score, which is your test statistic, how to calculate a t-score, is observed minus expected. Let's write that. The observed slope from your literal, from your least squares regression line, and the beta would be the expected slope if the null is true, so that's typically going to be a 0, over the standard deviation of the slope, S of b, or standard deviation of the slope. And those numbers will all be reported in your computer printout, and you're just going to pluck them out of the computer printout, paste them in, and be done with it. Because it's actually going to be computed already in your computer printout. You won't even have to pick up a calculator for this one. Degrees of freedom is n minus 2, where n is the number of x, y pairs in the sample. So the number of points. The number of points in your scatter plot, subtract 2. Basically, you're allowing one variable to vary for your x's and one number to vary for your y's. So take one of each variable out and you have 2 less degrees of freedom than you have pairs. Not really important that you understand why. You just have to know that that's what it is. So this is the same formula that we use for a t-score for t-test. We're just using slopes instead of means in this case. But the structure is the same. All right. When we do a confidence interval, and the conclusion we already know how to write. There is an association, there's not an association. So we're not even going to worry about that until we actually do an example. But we do also compute confidence intervals occasionally for linear regression. And the confidence interval looks exactly like a confidence interval for means. So you start with your point estimator, your observed slope. So that's the slope that you have in your least squares regression line, plus or minus a t-star with 2 less degrees of freedom than number of pairs. You can compute that using your inverse t command on your calculator. and this is the standard deviation of the slope, and that's going to be reported in your computer printout. All you have to do is pull the number out of your computer printout and stick it in there, and you're done. Okay, so super easy. It's the same structure as we use for all confidence intervals. We're just using slope instead of a mean or a proportion here. Alright, so there's all the groundwork. All that's left is to actually work through a couple of examples. Actually, we're just going to do one because they all look exactly the same. We'll do one together, and then you do some practice, as is our usual way of doing things. So this is an actual computer printout / everything embedded question that looks similar to what we have seen in the past on AP exams. So we're going to perform a hypothesis test and create a 95% confidence interval for slope for the anxiety and math test data. So this is tagging on to the worksheet that you've already done in class. So we did a worksheet in class comparing anxiety levels and math test scores, and we went back through how to write the equation of the regression line. We went back through what R means, how to interpret the slope, how to interpret the intercept in context. So all of that review stuff we've already done. So if you kind of hark back to what we did in small groups yesterday, this is just the next logical piece of the puzzle, and it's actually to run the test. So we are given, first of all, 3 pictures. And those 3 pictures are a picture of anxiety level versus math test scores. So this is X versus Y. There's the scatter plot with the line of best fit in it. Okay, there's no obvious curve there. There's a good bit of scatter, a good bit of residuals there, but it does look straight enough. But if I'm not really sure if it's straight enough, then I'm going to look at the residual plot. And in the residual plot, 0 line has been drawn in. There is not a particular pattern popping out. There's not a big curve popping out, not a straight line popping out. It's kind of random scatter, and there's no apparent fan shape. You really don't have a fan shape around that. So, straight enough condition, scatter plot is reasonably straight. The residual plot has random scatter and consistent spread from left to right. And then this last picture is a histogram of residuals. Okay, over here was residual plot, and this is a histogram of the residuals themselves. It looks reasonably unimodal symmetric. There's a little gap right there, but it's not a concern. That's not probably an outlier. Just because that's a gap doesn't mean we have a problem, because I can kind of picture a normal curve over that and it looks okay. So condition residual plot looks unimodal symmetric, no outliers. We're good there. So I'm already looking at these 3 pictures thinking my conditions are going to get met. And then I have all this computer printout. I have the dependent variable, that's the predictor variable, the Y is math test. Of course we could see it, the Y is on this original graph. That means your X is your anxiety level, your explanatory variable. We have an R-squared value. We do not worry about R-squared adjusted ever. Just don't even look at it. R-squared value, 0.276 is 27.6% of all the variation in math test scores can be explained by anxiety level. We have S, and that's a standard deviation. And then we have degrees of freedom, 24 points. We had 24 pieces of data, 24 students, minus 2 equals 22 degrees of freedom. So it's just a summary, a computer printout summary of a regression model that's been done. And then we have this business down here that we have to kind of sift through. So this middle section here, about regressions and residuals and F ratios and mean squares, that's not any language we've ever talked about before. So this whole little section here, we're going to just ignore it. We don't need it. We're going to ignore R squared adjusted. We don't need it. We're going to go back down to where we have variables and coefficients. So we have 2 variables. We have a constant, that's our y-intercept, and we have anxiety level. And anxiety level is our x variable. The coefficient of the x is this negative 4.482. So we've practiced plucking that number out of the computer printout before. That is your slope. That is your B. Okay, you're going to need that when you do your t-score. You have standard error of the coefficient, which means this number in the same line, that's your standard error of your slope. They're right there, next door neighbors. You're going to need both of those to get a t-score, and you're going to need both of those numbers to do a confidence interval. Then you have a t-ratio. That is your t-score. It has already been computed for you. Boop, boop. We just have to actually just copy it down. No calculator work to do. And then we have probability. Probability is a fancy word for a p-value. So this 0.0084, that's your p-value. Notice that I only care about the line associated with the variable that the slope is in front of. So I only care about that one line. Nothing else applies because everything in the top line is for your y-intercept. We are not doing inference on the y-intercept. We care about the slope. Is it flat? Is it not flat? That's all we really care about. And this is all the information that we need to do the mechanics for our test. So I'm going to keep that handy, and we're going to write up this test. So we're going to start with the null hypothesis. Null hypothesis is always the same. There's not a linear association. So there is no linear association between anxiety level and math test score. And the alternative, of course, is you take out the no. There is a linear association between anxiety level, don't do any dittos here, you got to write it out, and math test score. It's a little bit tedious, but it's not hard. Just do it. Alright, so simple to the point, always the same. The only thing that ever changes is your context on that last part of the sentence. And then we're ready to do assumptions, conditions. Our hope on the AP exam is that the problem stem says they've already been checked. Otherwise, we're going to write them out. So we're going to comment on these three pictures.
I just wanted to come say hi and bye.
Hi. I'm making...
And thank you for the only math class I enjoyed in high school.
That's very sweet. Let me...
Geometry, I can see it.
Let me... Okay. So now we're unpaused. Hopefully that didn't do anything terrible. So these numbers we're going to need when we do our mechanics, and so we'll come back to those in just a minute. So moving on to back to the assumptions conditions. I've totally lost my train of thought because I got interrupted. Sorry. Here we go. We were examining pictures. That's where we were. So no curves, no pattern, no fan shape, no outliers or skewness. So I just need to write that up in my conditions. But again, on the real AP exam, we hope that it just says they've already been met, and oftentimes it does, just for time constraints. So I'm going to comment on pictures. The scatter plot is reasonably linear. The residual plot, second picture, has random scatter and consistent left to right, that's an arrow, spread, no fan shape. And the third picture is the histogram of the residuals. So the histogram of residuals is unimodal, symmetric, with no outliers. So 1, 2, 3, 4 conditions checked in order, and the pictures of those graphs will always be in that order. So comment on 3 pictures, conditions are good. So it's not really so much a list you have to memorize as comment on all the pictures they gave you. And because we check those, we can do a linear regression t-test. Alright, so again, we hope that we have that statement that says conditions have been met. Often it will be there, so we always hope for that. So on to mechanics. Super short mechanics here, because all we need is a t-score, degrees of freedom, and p-value. So all of that was in our computer printout. We're going to pull that back out so we can reference it as needed. We have a hold on. Let me back up. So t-score equals, degrees of freedom was 22. 24 pairs of data minus 2 is 22. We need the observed slope. Okay, observed slope is the actual slope of the regression line, so the coefficient of x. That's negative 4.48624, negative 4.48624, and not knowing exactly how to round that, I'm just going to write the whole thing down. It's not going to kill me. Minus the expected slope. Well, in a perfect world, if there's no association, the slope would be 0. That second number is always going to be a 0. And then the standard error of the slope, well, that's in my computer printout. It's the next number. Standard error of coefficient is 1.551. 1.551. Now you'll find if you do that computation that it'll come out to be negative 2.89. It's already been computed for me. I just have to write it down. Negative 2.89. So almost 3 standard deviations below the mean. 3 standard deviations below the mean is kind of unusual, which means I'm probably going to reject the null here. But to be sure, we need the p-value. And the p-value is 0.0084. Again, that probability has already been computed for us. We just copy it down. That's below any reasonable alpha level, 1%, 5%, 2%, any of those. So now let's write a conclusion. This is not new stuff. With a p-value of 0.0084, we will reject the null hypothesis at an alpha level of 0.05, unless they tell us to use a different one. There is evidence of an association. So we're basically stating that there's evidence of that alternative hypothesis between anxiety level and math test score. So, no number crunching, no calculator required. Now, the calculator will do a linear regression t-test. You can put in a set of data, x's and y's, in a spreadsheet, run a t-test, and it will report all of these same numbers for you. But on the AP exam, you don't have time to type in 2 lists of data, and you don't have time to run all that on the calculator and pull it all together and write a conclusion. So everything we've ever seen on the AP exam is based on, they give you the pictures, they give you the analysis already done, and you use the analysis, the computer analysis that's given to write up your hypothesis test. Okay. Now, last couple slides, the confidence interval. If you have to write a confidence interval, sometimes we follow up a test with a confidence interval, sometimes we just do a confidence interval. There's a particular structure to the conclusion because we're talking about slope. So we're talking about rates of change. So we are blank % confident, whatever percentage you're using, 95%, 90%, 98%, that each additional unit of X in context, for us, anxiety level, for each increase of 1 unit in anxiety level is associated with an average increase or decrease. If it's a positive, it's an increase, negative, it's a decrease, between blank and blank math test score. So it's a little more convoluted, but we're going to do a practice one with this particular scenario. So let's do the confidence interval and summarize it. So the confidence interval, you would always start with checking conditions. We've already done that. Then you would name your procedure. So we'll use a linear regression t interval, because there's no reason to recheck conditions. They're the same for both. And then we're going to substitute into the formula. So the formula starts with an observation, a point estimate of the slope. So that's the slope from the least squares regression line. So that's that negative 4.48624. So the estimate of the slope from our sample, plus or minus t star. Now I need a t star for 22 degrees of freedom. Okay, that's a side trip. So let's do a side trip. T star for 22 degrees of freedom, we would use our calculator to find. So if we're doing 95% confident, which was what was in the original question, that means the middle is 95%, the middle section. We got 2.5% below, 2.5% above. To get the t-score, we need to use an area of everything below the t, which is 97.5%. So, inverse t command, let's pull that back up. So, menu, probability or statistics, either one, distributions, and inverse t will give us the t-score if we give it the area. So inverse t with an area of 0.975, 97.5%, 22 degrees of freedom, and that's 2.07. So we have a t-score of 2.07. So we're going to substitute that into the formula. And then we're going to multiply by the standard error of the slope, which was given in the computer printout. So that standard error was 1.551. Okay, so when you run this through with subtraction and run this through with addition, you'll get your two bounds. And the quickest way probably to do that at this point is to actually type it in the calculator. So type in this plus this times this, and then paste it back in with a minus sign to get your two boundaries. You know how to use a calculator, so I'm not going to walk you through that. But if you do this computation with subtraction, you'll get negative 7.70-ish. And do the computation with addition, you'll get negative 1.28-ish. And so we are estimating a slope of between negative 7.7 and negative 1.28, which means that on average, the math anxiety score, the math test score drops between 7.7 points and 1.28 points for every increase of 1 in anxiety level. So now we just got to put that into words, right? So we are 95% confident that for every increase of 1 unit in anxiety level, as x changes by 1, that's your change in y over change in x, so this is what y is doing. For every increase of 1 unit in anxiety level, the average math test score decreases by between, it's a decrease because these are negative, 1.28 and 7.70 points. And that is it. Last test, last confidence interval, and now we're just down to practicing. So we're going to call it done.